Hello, everyone. So let's start. I have a couple of things before we go into the lecture. So we released programming assignment 2 recently, and I just want to confirm this is a bonus assignment. So it's not mandatory. If you don't have to do it, perfectly fine. But if you do it, it's up to you. You can get bonus points for your programming assignment section. Okay. So if you think you're lagging behind in programming assignment 1 you didn't do well, and by the way, like, we will release the grades today, maybe midnight, for the programming assignment 1, but still I think you should have some idea like how you did, or you missed it, or it could be any other scenario. So I will encourage you to finish this programming assignment 2. That will help you in improving your grade. So this will be due on 15th of November, and strictly there will be no extension to this. All right, so if you want to do this, start it now. I just want to make it clear right now, please don't write to me to extend the deadline for this bonus assignment. Okay. So there is a comment from James. It's pretty easy. Everyone should do it. Yeah, if you think it's pretty easy, that's good. Of course, go ahead, finish that. Now, we will be releasing programming assignment 3 soon. And I just want to confirm with you, like, depending upon like what's your course load in other modules or other courses, when would you like to have this like released? So I have 3 options, either 5th of November, 8th of November, or 10th of November. And keep in mind, you have the bonus assignment as well during this time. And again, you will have roughly 2 to 3 weeks to finish this. So let me quickly. Okay, I think you should have to go along. Okay, question from Victor. When will we get the solutions for P1 in case we got it wrong? Solutions, I think we can release it. Yeah. So that's a good point. I thought we already did that, but let me confirm with TA, and I think we can release them today, like solution for both. Okay. Thank you for reminding. Then question from Victor, will you release the grades for both parts? So today we will release, I think for the first part, we are still working on the second. Okay, question from James. If the end date is the same, no matter what, the start date should be as early as possible. Yeah, the end date will change. Will change with the start date. So question from George, why not release it early and set a due date at the same time? We can do that, I mean, if you choose that. So, but again, it depends, right? Because some students might be busy during this time, so they don't want it to be released soon. So it varies from student to student. And keep in mind, you also have a project, the course project, right, during this time, which I'm assuming you're working on right now. Another question. P2 being a global uncapped bonus would be very, very good. Yeah, it will be a bonus just for the programming assignment, and there's a reason to it, and I think we have discussed that earlier. So because the students are coming from different background, right? Some are new to this kind of programming environment, so we want to accommodate them, and that's why we have this bonus. For everything else, midterm and homeworks, so I don't think that's an issue. It doesn't matter which background you come from. So that's the only motivation one. Okay. Okay, question from George. Is it 2 weeks after? So 2 to 3 weeks. So I don't know like the exact date, but at max it will be 3 weeks. All right. Yeah, that's fine. I'm not getting annoyed. If you have question, just let me know. I will try to answer it. Okay. Uh, Question from Sheen. Will the start date affect the due date? Yeah, it will affect the due date. Okay, all right. So I think I answered all the questions and we have the result for the poll as well. And I think most of you want it to be released at a later date. So we will release it on 10th of November. Okay. Share the results if you want to quickly go over this. All right, so that was programming assignment 3. And again, I'm hoping that you have already started working on a course project. So don't spend too much time, but at least do something daily. Maybe half an hour or maybe 15 minutes. It will help you like to make good progress in that. And the biggest, I think, benefit will be if you are stuck at some place, if you have questions, then we will be able to help you out. All right. So if there's any other question apart from this before we go to the lecture, please let me know. Otherwise, we are going to start object detection today. And this is kind of like one of my favorite lecture in this course. And there are several reasons, like we'll introduce several different concepts, which are most of which we have already seen. But the idea will be why those concepts are so powerful. They can be used like in a wide range of algorithms, wide range of problems. And that's what makes, I think, this lecture very interesting. So you will see. I think another question before we continue, when the PA1 grades will be posted and P2 cover the points needed for P3. Okay, let me read that again. When will PA1 grade? So as I said, we will release like for the first part today. And will PA2 cover the points needed for PA3? Yes, of course. So if you're not confident that you will be able to do well on PA3, then of course PA2 will also cover PA3. So it's for like bonus for all the 3 programming assignments. So it's your chance to get actually a perfect score for your programming assignments. All right. So we're going to talk about object detection, and we'll go over a couple of approaches how we can do this. So the first one will be sliding window, and I think now you should know what sliding window is. You have used this approach in, I think, almost all the concepts. HOG feature extraction, SIF feature extraction. We have seen in convolutional neural networks when you perform the CNN, the convolution operation in the CNN layer. And so again, it's the same concept, but you might be, I mean, it's interesting. It's being used like in almost all the algorithms, right? Again, we will use sliding window for object detection today. Then we will talk about image pyramid. And again, this is nothing new. So we have seen pyramid before when we were talking about, I think, SIFT feature extractor. There we were creating pyramid of images. And again, it's the same concept. And this is also interesting, how we actually evaluate how good an object detection model is performing. So it's not very straightforward, because in classification, the only thing you need to do is whether you predicted the class correctly or not. And then you can just compute accuracy based on whether the prediction was correct or whether it was wrong. So that's pretty straightforward. But in object detection, it's more complicated than that. And we will go over the full evaluation process. Right. So let's first try to understand what object detection is. So object recognition, we all know, given an image, we just have to say that whether a particular category of object is present or not. For example, if it's a person, if person is present or not. Now, object detection is something you have to perform classification, which means that you will have to say whether that particular class is present or not. In addition to that, you also need to tell where exactly that object is present in your input image. And that you can do like using different ways. The standard way is doing bounding boxes. So you just draw a rectangular boundary around the object, and you say that, okay, that let's say if you're doing person detection, you will say that person is present inside this bounding box. Okay, so this is one example, and again you can have multiple objects. For example, if you have two, you will draw two different bounding boxes. Okay, so that's the problem, and again there can be a lot of variations for even for person detection. I think there's a question from Mehdi. Does it have equal points to other programming assignments? Mehdi, I didn't get your question. Does it have equal points to other programming assignments? So yeah, I mean, it will be, again, it will be if your other, if you're saying like all three are of equal points, or if that's the question, that's true. Yes.
The question is that the programming assignment 2 is the same points, have the same points as the other programming assignments as a bounding point.
Right. Yeah, that's true. Right. So then you can have images, let's say, captured from UAVs. And in this case, you can see if we have to do human detection or person detection, you can see like these persons are very tiny, few pixels in this whole image. And again, this is the same problem, but much more challenging. Or you can have maybe videos captured from surveillance or CCTV cameras, which will be, you can say, kind of elevated from the ground. And again, you can have multiple people walking around. So you'll have to detect, or I mean, draw these bounding boxes around those persons. And this is kind of, again, challenging if you compare this with like ground level images, but not as challenging as this UAV images. So let's move on to like other object categories, because we may want to detect a varying range of objects, right? It doesn't have to be person all the time. And we have seen this image earlier in this course. So you can have multiple objects, you can have a bottle, a laptop, and you can see it's kind of very cluttered, right? But as a human, we can easily draw all these boundaries. We can say this is a table, this is a ball, or this is a cup, bottle, laptop, right? Pretty easy for us. But later we'll see like how it's very complicated for the computer or for your AI algorithm to do this. So you can have a complex scene like this. And again, the problem remains the same. You have to classify the image as one of the object categories. So in this case, let's say these are maybe how many, 5 or 6 different object categories, right? So your network will say these 5 objects are present. And in addition to that, it will also say, okay, this object category, what are the bounding boxes? And not just like what are the bounding boxes, it will have to say how many objects. For example, you have 2 different bottles, right? So you'll have to separate these 2 instances. So I think the motivation, it's clear why we need object detection. I mean, one good example could be self-driving car. So if you have an automatic car, then it needs to detect like what objects are present in the road, on the road, right? If a person is crossing the road, or a dog is crossing the road, then it needs to first of all figure out if such objects are present on the road or not, and then it needs to locate exactly where on the road they are, and then it will make decision whether to drive or whether to stop. So this is one good example. So I think that's sufficient to motivate why we need to solve object detection. Now, before diving into the more complex solutions, rather I will say they are not complex solutions. They are also very simple solution and pretty powerful, but a bit more detailed. So before diving into those, let's briefly talk about a very simple solution which we have covered earlier as well. So again, this is using sliding window. So what we can do is, let's say this is your image, then you can actually come up with a box, and that box is kind of trying to detect whether a particular object is present or not in any image. Okay, and then what you do is you just try that box in all the possible locations in your input image, and for each box you have to just perform classification task, and classification you already know how to do it, right? So you just have to classify whether, let's say if it's person detection, you take this bounding box and take that patch and pass it to a person classifier, and it will tell you whether person is present or not. and then you slide over this window in all the regions in the image, and using just that classifier you will be able to localize where exactly a person is present or not. Okay, and this approach, I think there are a lot of papers, but I think the most impactful papers, I will say these three. So starting from 2001, then 2005. And so the first one was like this Oira Jones. This is very popular paper. You can see like 22,000 citations. It was used for face detector, whether face is present or not. All right, again, the same approach. You just take a window and keep sliding it in the image. Then in 2005, it was used for person detection. And this algorithm you have already studied, the histogram of gradients, right? So there what they did is they took this sliding window approach, and for each window, they extracted this histogram of gradient features and then used those features for classification, whether a person is present or not. And then again, this is more advanced. It was in 2010, 2010. So this was kind of deformable part-based model. Again, it was using this sliding window approach. So the very basic approach you can do is we can just use a template. I think we covered this in the first lecture. So let's say this is the template of a chair and this is the target image. What we can do is we can just match this image at all the possible locations, find the similarity, or you can say correlation between those two, the template and the patch, and you will have some kind of correlation, and depending upon like the outcome, you can say that okay, a chair is present. But the issue is if you use this like in real world images, because there can be a lot of variations, it won't work. It will certainly fail. So this is an outcome if you try the same template on this image, and it's very hard to see or hard to say a chair is present. Okay, and again, this is pixel level matching, and that's one of the reasons why it's failing. Okay, so now let's see how we can use sliding window very effectively where it doesn't fail. And I will first cover a very general approach, and then you can have different varieties of that. Okay, so a general approach, what it will do is it will take a bounding box and it will scan all the possible locations in the input image. Okay, so that's the first step. The second step is for each location, you will extract some set of features. And again, these could be like any set of features you want. You can extract SIF features, SURF features, HOG features, or you can even use your deep networks to extract the features, maybe autoencoders, right? So it doesn't matter. So that's the second step. And once you have those features, you try to classify those features as one of the object categories. For example, if it's person detection, you train a classifier which will take in those set of features and say that, okay, whether these features belong to person or not. And then finally, it's post-processing. You will see why this is very important. It seems like just processing, but it's not processing. It has a very big role. And even a lot of algorithms today like use this kind of post-processing. So those are the main 4 steps. Let's walk through like all these in more detail. So when I say scan all possible locations, mean you know how to do that. You have done that for your programming assignment as well. So you have a detection window and it will have certain size. You will start sliding it maybe in the X direction and then in the Y direction, and keep sliding it until you reach the last location, right? So that's pretty simple. Now, one issue here is the size of this window is fixed. It's not changing. And that's what you have seen in most of your algorithms earlier. And that's a big issue. So let's try to understand why that's an issue. That's an issue because if you are capturing, let's say, just people in one of your images, they can have different kind of resolution or different aspect ratio, right? So they will come in different sizes. For example, if you just observe this particular image, and this is just one location, you can see that the person who are like closer to the camera, if you look at the resolution on the image level, it's much bigger than if you compare that with the person which is like far away from the camera on the background. So for example, this person here, if you try to draw a bounding box, it's pretty small. Okay, So that's the issue of scale, and we have talked about this before as well. We can have multiple scales. Now the question is, how do we address it? And there can be like a lot of solutions. I will just talk about one very simple solution, which actually is very effective and it works. So what we do is we just downscale the size of your image. So earlier, let's say this was the original resolution. I just reduce it to half. So when I'm reducing the size of the image, I'm not reducing the size of the bounding box. It still remains the same. Okay. And I keep doing that until I have the smallest resolution. Okay, I will keep shrinking. And what will happen when I'm doing that? Let's say this is the original resolution and this is the detection window. What will happen is I keep shrinking in half, and this is called a scale space pyramid. And you have seen this pyramid in SIF feature extraction as well. It's almost similar. Okay. Now, what's going to happen here is if you have a person like of a which is covered by a big window, in the top one it will be covered with a very small window. So then if you are just using the same detection window, if you use the same window on all the frames, you're kind of covering all the scales of your objects. Okay. Now, okay, there is a question. Could it be possible to treat humans in the image as features and extract them, or would it be complete? Possible to treat humans in the image as features. Yeah, we will do something like that, but so once we draw the bounding box, we are actually going to extract features from that location. And okay, so I think I get your question. So you can treat that as an image as well, but that won't work. And it's the same reason I showed you like a very simple approach for object detection, because if you do that, you can have a lot of variations, right? Even in humans, you can have a lot of variations. So if you just use that patch as feature, so because there will be a lot of variations, it will not be robust. So that will be a case similar to this. And that's why we extract features from this instead of using the patch itself as feature. Okay, so there's one more question. Probably maybe means, can we design filters that can give high response in an image where there is a person? Okay, so I didn't see that question from Mehdi, but anyways, yeah, you don't want to design those features, because in CNN you learn those filters, right, automatically. And designing such a filter, it will be too complicated, right? Because it's not a very simple structure. It's not like you have an edge or maybe a circle, very small pattern. So even if you have, I mean, one thing you can do is you can have a kernel, a very big kernel, where you just draw maybe the boundary of the person. I mean, that might work, but again, it won't be very robust. Okay. So you can think about like how you learn your kernels in your CNN, right? You don't try to learn very big kernels. And the reason is those kernels cannot be generalized across objects. And you don't want to learn too many big kernels which are specific to one object category, right? And that's why we try to learn smaller kernels which can learn patterns of features which can be shared across object categories. For example, if your kernels are just learning edges, right, then most of the objects will have edges. So those kernels can be shared across categories. So that's the beauty about learning those kernels. Okay, so I hope it is clear now. Go back. All right, so now what we do is when we are creating that pyramid, that scale space pyramid. Each time we are just replacing, we are just reducing the resolution by half. And this is like one simple example. And so what we do before resizing, we actually perform some kind of filtering. It could be Gaussian filtering maybe, and then we resize, because there are like a lot of issues during resizing. It's not that straightforward. Either you can do interpolation, or you can perform sampling when you resize, right? So by sampling, it could be, you have, let's say your resolution is 100 cross 100, all right, and you want to go from 100 cross 100 to 50 cross 50. It means that for 2 pixels you just have to pick 1 pixel. So either you can do interpolation, or you can just average two neighboring pixels, and again, mean that's not always a good thing to do. Or you can just pick 1 pixel out of those two, so that's called sampling. So you are picking 1 pixel and skipping one, and mostly that is used because then you are actually preserving the actual values, actual pixel values in your image. All right. Now what may happen is that if you're just skipping pixels, then you might also be losing information. And to avoid that, we actually perform filtering. And filtering is kind of, you're blurring your pixels, right? So you're actually using information from your neighboring pixels. So even if those pixels are getting ignored during sampling, we still get like some part of that, because when you use Gaussian filtering, you use neighboring information from neighboring pixel, right? So that's the intuition why you perform filtering before reducing the resolution. And so this is like again the same example, but showing you like this is kind of upscale version, but again just for visualization, and you can see that how the quality is actually going down. Okay, so one interesting thing here is, so this is the main motivation why we actually need a scale space pyramid. So this was the original image, and each time we are actually reducing it by half, and you can see that at this resolution 8 cross 8, we can hardly see anything, even in this one. All right, but if you look at these images, I mean, some kind of structure is still visible. You can see that pattern. You can see that it could be some kind of nose. All right, so why this, how this pyramid is actually handling scale. If you look at, I think it should be here. Yeah. So if you just look at one bar in this image, so one horizontal line, right? So this is kind of covering the nose of this zebra's mouth, right? Just one pixel. But if you keep increasing the resolution, then it's going from nose to hair. Okay, and that's what is important, because your window size when you're trying to extract features, it's not changing. So it means that the same window will extract feature of nose from this smaller patch, and it will extract feature of a hair from this high resolution image. Okay, so the same bounding box. Now let's try to understand how this pyramid is constructed. So as I said, mostly sampling is used, and this is just one-dimensional example. And again, you can generalize this to 2D because your images are 2D. So these are your, let's say these are your pixels, neighboring pixels. All right, and again, this is just one-dimensional. Now the first step is you actually perform filtering. So this could be Gaussian filtering. All right, so when you perform filtering, let's say this is your width of the filter, then the value at this location will have information from all the neighboring pixels. All right, so that's the first step. The second step is you actually perform sampling. So what you do is, when you do sampling, you actually skip one of the pixel values. So you pick this one, you skip the next, you pick this one, skip the next, and again picking this, so on and so forth. And in this one, you can see that in this one, the resolution was 8, right? 8. These are 8 pixels, and you reduce from 8 to 4, or 8 to 5 in this case. So right now you just have 5 pixels. All right. And you just repeat this process. Again, you will perform filtering on this small resolution. again you will perform subsampling, something like this. Okay, so that's good. So one interesting fact about this is, if you compute the memory consumption of the whole pyramid, which has multiple resolutions, it will only take like 4/3 of the original image. So it's not a huge, it's not taking huge amount of memory. Okay, so that's a good point. So that will handle the case of different resolution. But what about the aspect ratio? So for example, we could have like image like this. Let's say this is a person and you want to detect this. So your window size is something like this, but your person in this case, it's a different aspect ratio altogether, right? Even if you try to build different scales, so what will happen is this bounding box will never fit perfectly over this person because the aspect ratio is not matching. All right, so that's again an issue, but let's not worry about that now. But again, so that's something which this scale space parameter is not going to fix for you. Okay, so that was the first step. Let's move on to the second step, which is feature extraction. And this is pretty simple. I mean, once you have all those locations, what you do is for each location, you just extract the features, and it's up to you which algorithm you want to use. You can use HOG, you can use SIFT, or you can use like any other algorithm. All right. So if it will be HOG, then you know that you can compute edges using filtering for your image. And so this will be your one location for that window. And you slide it and extract features for all the locations. And the way you do that is, let's say this is your one single block. Then for each block, again, you will divide that into different cells, right? And then for each cell, you compute the histogram, that bin, and then you just concatenate the bins for all the cells, and that will give you one set of features, and you can normalize that. So you understand like all this process. We talked about this when we were covering histogram of gradients. All right, so that's the second step. Now the third step, again, you know this classification. What you do is, of course, like to train such a thing, you need annotations, right? And if it's object detection, you need annotations on your training samples, which means that you need those bounding boxes. Then what you can do is use those bounding boxes and extract all these positive patches. And in these patches, you know a person is present. All right. And then what you can do is, for all the locations where we had no bounding boxes, we know that it doesn't belong to person category. So we can take those as negative samples, all these patches. And then we use the second step, extract features for like positive samples, negative samples. And once we have those two, we can easily train any classifier. It could be your neural network, it could be your CNN, convolutional neural network, or it could be as simple as linear classifier. All right. So that's also good. And then you run the classifier for all the scales for the full pyramid. Okay. Then the next thing is, I think, post-processing. So yeah, once you do that, you will get a result something like this. All right. So what's happening here is you scan all the locations, you extract features from all the locations, you train your classifier, and then you use the train classifier to actually predict which of these locations is actually positive, which is negative. And this is the result. So all the yellow bounding boxes is saying that a person is present, which is kind of right, except for this one. Okay, which is fine. It's not perfect. Now, once we have this, still the problem is not solved. Because if you think about this, I mean, if you ignore this, that's fine. Even if you look at the positive cases, for this person over here, we are getting how many? 3, 4, 4 different bounding boxes, which is not correct, right? We just need one bounding box around this person. And same is happening with most of the other people here. And the reason is, when you're sliding your bounding box in your input image, then the features are not changing a lot. because if you just shift by maybe 2 or 3 pixels, you might still get the same set of features, and your classifier is still doing the right job. It's saying that this is a person. It's not making any mistake there, right? But again, it doesn't matter if it's not making a mistake. I mean, this is not right. So how we can fix this is this post processing. As I said, this is a very important step. All right, so there's a question from Fatima. How do you determine the size of the bounding box? So the size of the bounding box is your window which you're sliding over your image. Right, so we choose one bounding box and we were just sticking with that and sliding it over. So we'll just use that that size. And in this case, you can see that these bounding blocks are smaller because these might be coming from a different level of a pyramid. Is it clear, Fatima? I mean, essentially, you just have one size, but if you apply the same size on a smaller resolution, it actually means a bigger size, right? Because you'll have to scale it back to the original image. Okay, let me try to explain maybe on the sketchboard. So can you see my screen, the whiteboard? Okay. So let's say this is your image and this is a person, all right? And this is a different level in your pyramid, the resized one. And this is the person, right? Maybe a little smaller. Sorry, my drawing is not good. All right. Now, let's say I start with a bounding box of this size. So I will scan it all over the image, right? And at this location, I might be scanning maybe this part, or maybe this part, but I will not get the person because it's just part of the person, right? Now, what I'm going to do is I'm going to use the same size on the smaller resolution, something like this. Right? But when I put that box on this person, I get the perfect person. And then you can say that, okay, this is a person. Now, the detections I'm showing you, that's on the bigger image, right? So like this is a person. So I take this size, I take this bounding box, and I know, let's say this is 100 cross 100, and this is 20 cross 20. Again, this is 100 cross 100, right? So let's say this bounding box was maybe 8 cross 4. So again, this will still be 8 cross 4, right? But going from 20 to 100, it's like 5 times, right? So when I have to plot this bounding box on this image, it's going to be 5 times. So I will just make it 40 by 20. So it will grow, but it will perfectly fit on the person. Is it clear? And let's say you have another example. You can have a person on the back, and this bounding box might be fitting it perfectly. Then, so this scale is similar. This is 100, this is 100. So you can just directly use the scale. So you will have a bounding box here for resolution 8 by 4. Okay, great. So let me go back to this slide. All right. Right. So now using these 3 steps, we get all these boxes. Now, what we have to do is perform some kind of post-processing so we don't have those duplicate boxes. And what we do is we do non-maximal suppression, and you already know that algorithm, but it will be slightly different in this case, but the idea remains the same. So you will see, like, throughout the course, there are concepts, like only few concepts, but the same concepts are getting used again and again. Okay, so we'll use non-maximal suppression. And you know that the idea is, so this is coming from the edge detection where you used it. Let's say if this pixel was detected as an edge, to actually confirm if this is an edge, you look at the neighboring pixels and see if they are also detected as edges. And if they are detected as edges, you compare the magnitude. So you only consider this one as an edge if the magnitude is greater than this one and this one. Otherwise, you just suppress this point. You say that this is not an edge. Okay. In that case, either this one or this one will be the edge. So the idea remains the same. In this case, you're looking into bounding boxes. So what you do is you just have to iterate over all the detections, and your algorithm will have to say that, okay, how confident each detection is. So you will have some kind of probability score for each box. All right. So then what you do is you just sort all the bounding boxes depending upon the confidence score. So you start with the bounding box which the network is most confident about detecting that particular object. All right. Then what you do is you try to find the overlap of that object with all the other boxes. All right. And overlap, again, this is a new concept. I don't think we have covered this earlier. Again, this is a very powerful concept. You will see it's used very widely in computer vision. So this is called intersection over union. And the idea is you take the ratio of area of overlap versus the total area of the union. For example, in this case, we are looking into bounding boxes. So let's say this is your first bounding box and this is your second bounding box. So you will figure out like what's the intersection, what's the common area between these two. So this solid blue region over here, so that will go into the numerator, which is area of overlap. And this is like the sum of area of both as an union. All right. So again, the solid area. So that will go into the denominator. That's the area of union. And this ratio is called intersection over union. So what you do is you pick the highest scoring box and compute its intersection over union with all the other boxes. Okay. And if other boxes are actually overlapping with a high amount, you will remove those boxes. So for this, you will need some kind of threshold. And usually we use like 0.5 threshold. So if it's greater than 0.5, we say they are overlapping. We'll ignore the other box. If it's less than 0.5, we'll still consider that, because sometimes what may happen is you might have objects which are overlapping in your input image. So let's try to understand that in this image. So let's say this blue box over here, it has the maximum probability. So we'll start from this, and then we will compute the intersection over union of this box with all the other boxes. So you can clearly see that if you talk about all these boxes on the right, the intersection over union is 0. So you don't have to remove these boxes. But if you look at the intersection over union of these neighboring boxes, right, which are close by, then they might have intersection over union which is greater than 0.5. And if it is greater than, you will just drop those boxes. You will say they are not the predictions, they are just duplicates. And in this case, what will happen is then all the other boxes will be removed because the intersection over union was greater than 0.5. Then you keep repeating that with all the other boxes. So then you will go to the next list. In this list, the box with the second highest probability score. And then again, repeat the same process. All right. Okay, question from Carlos. What determines the highest score box? So when your network is making this prediction, it will have some kind of confidence score, some probability. Okay. And I mean, for example, in this case, let's try to understand. So in this case, let's say we use a simple classifier. Right? So classifier in this case will be a binary classifier. So you feed in the features and that classifier will say whether a person is present or not. And again, you know that the classifier will predict either 0 or 1. If it's close to 0, no person. If it's close to 1, it's person. So it will never be perfect. It will never be 0 or 1. It will be some number between 0 and 1. And you can directly use that as a confidence score. let's say it may happen that for this bounding box, the score was 0.98. So you can use that as a network's confidence. Is it clear, Carlos? Okay, great. All right, so then you can do the same thing for the next one and keep doing that. And eventually you will have your final result, which will say that, okay, given this image, your algorithm is saying all these are person. Okay, so that's like the full process of object detection. Now, the final thing is, once you have these results, how do you know your network is actually performing good? Because as a human, I can say that, okay, it's still missing in this person over here, this person, and the person on the back, and this is a false detection. So then we need some kind of metric or some kind of measure which can say that, okay, how good your network is performing. So that's the next topic which we are going to talk about. And a question from Shah, how do you define this notation? Yeah, we haven't talked about MAP yet, Shah, right? So I don't know why you asked this question. So probably when we have talked about MAP, then I think we'll talk about exactly, I think, what you're asking. So I think it would be good if you ask it at a later time. If I forget, I will keep in mind, just in case I forget. Okay, please remind me, okay? We'll go over this. And that's exactly the next topic. Okay, so let's first quickly review like the concepts which we need to compute that metric. And that metric, as Shah was saying, it's mean average precision. So we need some concepts before that. So we'll quickly go over those. So the first one is intersection over union. You have already seen this. So, but that was your non-maximus suppression, right? So that was a different part of the algorithm. This is the evaluation, but again, the same concept. So again, you have to compute intersection over union, and you know how to do that. So let's say this is the ground truth, the red one, which is detecting this car, and this purple one is your detection, what your network predicts. So what you will do is you will compute this IOU score, which is the area of the yellow rectangle, which is kind of overlap between these two. And the denominator is the union, the blue region. Okay. So ideally what we do is we set a threshold, because we can't do it for all the thresholds. And usually we set a threshold of 0.5. All right. So we say that if IOU, this overlap, this intersection over union score is greater than 0.5, then that's kind of a right detection. It's not perfect, but it's kind of right. But if it's missing this threshold 0.5, then it's not a detection. Okay, we will just ignore it. So that's the first term. And make sure you understand this, because this will be very useful when you compute the final metric. Okay, so these are some sample IOs just to give an idea. So in this case, you can see that even though the overlap is perfect, right? Let's say the green one is the ground truth, the red one is the predicted one. So you can see that, I mean, it's a very good prediction. I mean, you can have like such kind of error from a human as well, but still your IOU score is 0.9. So it's not perfect. So which means that your IOU is actually very sensitive. And in this case, if you are slightly moving it to the right and to the bottom, then you can say that it's quickly dropping to 0.53. And our threshold is 0.5, which means that if you slightly move it away, something like this, you are missing that threshold. And what that means is, if this is your actual object and you predict this one, then it's not a right prediction. Okay. And again, as you move it away, the IOU will drop. And in this case, it drops to 0 because they are not overlapping at all. Okay, so that was IOU. Then based on that, we'll have some other terms. And you might have learned these like in machine learning course. The first one is true positive. True positive means whatever you are predicting, that's actually matching with the ground truth. So in this case, let's say the red one is the ground truth and yellow is which you have predicted. And in this case, we are assuming that the IOU is actually greater than 0.5. So we predicted bird, and the ground truth, we can see it's a bird. So that will be counted as a true positive. The second thing is false positives, which means that you are saying that it's correct, it's a detection, but it's a wrong detection. Right? So these are all the categories which fall into false positive. So let's say red is the ground truth bounding box, and yellow is like something which you have predicted. So the IOU is perfect, it's greater than 0.5, but the class category is wrong. This is a bird, it's not a cat, which means that it will go into false positive, even though the overlap is perfect. Okay. Then the other category is when the IOU is actually pretty low, less than 0.5, or there is no overlap at all. Then the last one is false negative, which means that there was some object present and you were not able to predict it. So that will go into false negative. And you need these three to compute a number which is called FN score. But in this case, we will not use FN score. That's what you do like in your classification problem where you have multiple classes. So in this case, let's try to understand that maybe with this example. For example, if this is a person, and so this is after your NMS. So after performing the post-processing, you still get these two bounding boxes because the IOU was not that high in this one. So then only one of these will be considered correct. So let's say if you are saying yellow is the correct, then orange one will have to be false. It will go into false positive. So only one detection can be correct. Okay. So otherwise what we can do is we can detect like all over the place these bounding boxes, and one of them will definitely match with the ground truth. So once we have those scores, we compute two things. The first is precision, and the second is recall. And again, you should know this from your machine learning course. So precision, as the name says, it is about whatever you are predicting, if it's correct or not. Okay, so if it's right, then you will have high precision. If it's not right, you will have low precision. So that's the concept, but you can use these numbers to actually compute it. So precision is computed at true positives over true positives plus false positives. And again, you can think about this because true positive is something which you predicted. False positive, again, it was false, but you predicted it, right? So that's the total number of predictions from you. And out of these, only these were true, which means that whatever you predicted, whether it's true or not, that will tell you the precision. Recall, on the other hand, it measures something else. It tries to measure whether you were able to detect all the objects or not. So it doesn't matter whether you are predicting correctly or not, because that's the role of precision. Recall is all about whether you're able to predict everything or not. It's kind of greedy, right? So let's look at the formula. So again, you look at true positives, what you have predicted correctly. And in this case, you're adding all the false negatives, which you were actually not able to predict. So which is kind of giving you all the objects which were present in your data set. And out of all those, you only predicted true positives. So this is telling you like how many portion of those you were actually able to predict. Okay, so these two are actually measuring two different things. And we will use both these scores to compute MAP. So how we compute MAP, yeah, I think we have time, we can go through this. So what we do is we sort all the predicted boxes for all the images. All right. So let's just focus on one particular category. Let's say person. So whatever bounding boxes your network has predicted as person, you will take all those boxes from all the images, sorted according to scores. Again, the same probability scores. And then what you're going to do is for each location in that sorted list, you're going to compute recall and precision. Okay. So I think there is a question from false negatives were the objects that were detected but not classified right. False negative. False negative were never detected actually, because that's a negative which your network is saying a negative, but it's actually false, right? So your network missed those objects. So let me go back to this figure. So in this case, this is the, let's say this is the image and this is the ground truth, and your network is saying, okay, no object is present. then you actually miss this one. In fact, if you look at this, if you just focus on this one, this is also false negative because your network is not predicting this. Is it clear, Matt? Okay, good. So ideally what we want is, we want high precision, which means we want like 100% precision. We want to be correct every time, and we want a very high recall. We want recall to be 100% because we want to recognize, or we want to detect all the objects. So if we do that, it means your algorithm is perfect. But obviously that will never happen. Okay, so this was fine. You create a list, and for each location in this list you compute recall and precision. And once you do that, then you can plot this precision recall curve, because your recall will vary, right, as you move down the list, and your precision will also vary. Okay, so based on that variation, you will connect these dots, and you will get a curve something like this. I will talk about more how you can draw this curve. But the idea here is, what we want is, we want very high recall and we want very high precision. But this curve is showing like how your recall is changing when you are changing your precision. Okay, and that's actually a good there's a trade-off between these two, because what you can do is, essentially you can try to predict a lot. If you do that, then you are improving your recall. All right, but on the other hand, if you try to predict a lot, then it may happen that in those predictions you might make incorrect prediction and your precision will drop, right? So there's a trade-off. And so that's the, like, when you're trying to favor recall. But the other direction could be, you can try to favor precision as well. In that case, you may want to predict maybe only few objects where you're very confident. And then when you do that, then you will say that, okay, whatever you predicted, that was correct, which means you will have high precision. But if you do that, then you will not be able to detect like all the objects which were there. You will miss most of those. Then you will have a very low recall. And that's the trade-off. All right. So yeah, I think there's a pop quiz. The question is, so let's say you have a precision recall curve and two different variations, A and B. So A is one particular example, B is the other. So again, this is showing performance of like two different architectures. And the question is, which one of these two is actually a better network, which is doing a better job? Okay, I think that was enough time. So in this case, like if you look at these two plots, so let's consider one point. So at this particular point, you can see that, okay, let's just focus on one recall level. Let's say 0.5, somewhere here, right? So when your recall is 0.5, which means that both of the algorithms have the same recall, right? It's 0.5, we have selected that. And then if you try to see what's the precision, you can see that the precision of B is pretty low, right? It's, let's say, 0.8 or something, 0.7 maybe, but the precision of A is actually much higher. And that's actually consistent for all the recall values. So whichever recall value you pick, your A is always giving you higher precision. And that's the reason A is actually better than B. Okay. So And in reality, you will never get like precision recall curves like these. Your plots will be more like this. And this curve will be is actually used to compute first it's used to compute average precision, and it's called average precision because you have all these precision values, right? At for each recall you have some precision, and then what you can do is you can actually compute an average of all those precisions, so that will be known as average precision. And then you compute that average precision for all the classes in your data set, and then you take a mean of all those. So when you take mean across all the classes, that's called mean average precision. Now we are going to go into detail how exactly we compute this number, because it's it's a little complicated than that. But let me answer. I think there was a question from Shane. Yes, A was the answer. Daniel, the AUC is better. The model is better. Yeah, that's true, Daniel. So AUC is in area under the curve, and we'll talk about that. So there was a question from Shah, which was saying mean average precision with some range, right? So that so now you understand mean average precision, Shah, right? And that at the rate 0.5 to 0.95 is telling you the threshold you are using for your IUU. Okay, so you can use a IUU of 0.5. You can plot, you can create such a plot, compute MAP. Then you can create you can set a threshold of maybe 0.5, 0.55. Okay, so we'll have some step. I think usually for MS Cuckoo they use a step of 0.05. So you move from 0.5, 0.55, 0.50 all the way up to 0.95, and that average will give you this particular metric. So I hope that was clear now. So Shah, that was a question, right? Okay, good. So I think how to compute this score, we'll talk about that maybe in the next lecture. That might take some time, and I think there will be a lot of questions after that. So we can end it here now. If there are any other questions from the lecture today, please let me know. Otherwise, we can end it here. Yeah, that will be fine. As long as you are using like some portion, some maybe training set or maybe some testing set where you have multiple objects, then it should be okay. And I'm assuming that you are doing this alone. Good. So question from Fernando, can we use a different distance measure for our KNN? Yeah, I mean, you can use whatever you want, but the result won't change because it's nearest neighbor, right? It doesn't matter which metric you are using. If some point is close to another point, I mean, it will still be the closest. It won't be like you're using L1 norm, it will be closer, or if you're using L3 norm, it will be far away. So you can try it out. That's pretty interesting. But yeah, of course, you can use whatever metric you want. Okay. So yeah, it seems there is no other question. So then let's end it here. I will see you next Tuesday. Bye.